Okie dokie. Here we go with Notes Week 3 Part 2. We are talking about free fall. So here is a base jumper with no chute and free falling towards Earth. Okay, so the idea behind free fall is that there's an object and the only force acting on that object is gravity. That's the definition of an object that's in free fall. We definitely neglect air resistance, and for something like a base jumper that would be a very large approximation, so not a good approximation. But for objects in the classroom, such as tennis balls moving at low velocities, air resistance is negligible. So basically just keep this in mind, okay? Air resistance, negligible, if I can spell that correctly. Negligible meaning we basically disregard it, okay? And a lot of our calculations will still work out. So the acceleration due to gravity in Earth's gravitational field near the surface of Earth is, we say, negative 9.8 meters per second, which is the same thing as negative 9.8 meters per second squared. And so yes, this is a thing, writing the seconds squared because it's per second. The negative sign simply indicates direction, and so if we were to draw arrows indicating the gravitational field near Earth, it's very strong. It turns out that the farther you get away from Earth, the less gravity pulls on you. And hopefully this makes sense because, you know, we are being pulled towards the sun, but our planet experiences a force, but we, you know, when we're sitting on Earth, we feel the pull due to Earth much more than the pull due to the sun, yet the sun is a much larger mass. So that's simply due to the fact that we're so far away from the sun. So notice how I'm drawing these arrows, and the arrows are getting smaller as I get farther away. So we could generalize this by saying something like gravity strongest near surface of Earth. And we'll talk more about gravity later. But when we say negative 9.8 meters per second squared for the acceleration due to gravity, that's the acceleration due to gravity on the surface of Earth. Farther away it would be less. And so free fall, I sort of described the definition up here. I'll write it. So when an object has only one force acting on it, we'll say acting upon it, and that is the force due to gravity. So when you throw a football, a marshmallow, anything like that, it is a projectile and it is in free fall. It doesn't have to be falling straight down. Okay, hammer feather video. This thing's amazing. Let's turn the page and hope that they're... So here we are, and I think this is going to work. Maybe not. Okay, so this is not... Ooh, here it goes.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Proves that Mr. Galileo was correct in his findings.
Okay, so that was pretty amazing. So let's do a calculation here. Here's our favorite physics student, Joey, again. So Joey throws a rock upward with a speed of 25 meters per second. Okay, straight up, vertical velocity. We want to know how high does it go, how long does it take to reach its maximum height, and how long does it take to land. So These are the hints that I give you and have given you. Draw a diagram, list what's given, what is assumed, and what are we looking for. So here's our diagram. I'm going to follow instructions. So we have Joey, and you know Joey is throwing this ball. Joey's got really long arms because he is throwing the ball from the ground, an initial height of 0. And so it goes upward, and maybe I would draw some arrows. Notice how the arrows are getting shorter, okay? And then on the way down the ball speeds up. And what we know, so if we were labeling this diagram, we might say initial velocity, we know 25 meters per second. Up at the top, because we are interested in that point, we know, that the velocity is 0 meters per second. Everything else we don't really know. We could call this the height. I think we're interested in that. Put a little question mark by it. We don't know time. Okay, so there's a diagram to help me consider with poor Joey's long arm there because he has to throw from the ground. So if we were listing the given information, we can say let's take a look at the first thing we're trying to solve for. How high does it go? Okay, so we're talking about how high does it go, and so that point up there, I'm pointing up here. So our final position is, we don't know, that's what we're looking for. Our initial position, or the rock's initial position, is 0. It starts on the ground. The rock's initial vertical velocity, 25 meters per second, so that's a positive quantity. It's assumed that this takes place on Earth, so we know that the acceleration is negative 9.8 meters per second squared. Okay, so notice how the question did not tell you the initial position is 0 meters, and it didn't tell you the acceleration due to gravity is negative 9.8 meters per second squared. These are things that you gather from the situation. So if we want to know how high does it go, I think that notice how we don't know time, and we're so far not asked for time. So using this information, we do have an equation, and it looks like this. So final position equals initial position plus initial velocity times time plus 1/2 at squared. And if we substitute in, given these values, I can tell I'm going to need a calculator here. We can say x, final position, equals initial position plus initial vertical velocity. We don't have time, so this is not going to work. Here's what I meant to say. Final velocity squared equals initial velocity squared plus 2a, and then final minus initial position. So let's see if this works. We know, we also know this, and that is that at the top of its flight, or trajectory or whatever you want to say, the final velocity of the rock is 0 meters per second. So that's more hidden information. It was looking a little skimpy here, so we do know this. Okay, so our final velocity squared, 0 squared, our initial velocity is 25, our acceleration is negative 9.8, and we have our final position minus initial position like this. So solving for x, let me grab my calculator. We're going to subtract 25 squared and then divide by negative 19.6. So 625 divided by 19.6 gives us 31.9 meters. So that's how high it goes. Okie dokie. Second part of the question asks, how long does it take to reach its maximum height? So I'm going to show you a trick, and then we'll write down our given information and all that kind of stuff. Okay, how long does it take to reach its maximum height? So when something is thrown into the air, okay, it goes up and up and up, and then comes down and down and down. And when we talk about this number, negative 9.8, what this means is that, and I'm going to write this in words because it's kind of a key concept. What this means is that object loses 9.8 meters per second of velocity every second. So I could draw out a table and it might help this make sense. So time, velocity. So when time starts, the velocity is 25. After 1 second, we're going to subtract. So this is going to be 25 minus 9.8. And this, after 2 seconds, is going to be 25 minus 2 times 9.8. And so it's going to lose 9.8 meters per second of velocity. So what would this be? 15.2. And this would be 5.4. And so you see, somewhere between second 2 and second 3, it will have attained this vertical velocity of 0. So the trick is you do the initial vertical velocity divided by 9.8, and that equals seconds, or time, to max height. So this is kind of the easier version where, and I'm typing this into my calculator right now, 25 divided by 9.8, and so we're getting 2.55 seconds. So we could say, and this is time to maximum height, all right? And that's our trick. If we were using an equation, I think the top equation on your formula page shows that the final velocity equals initial velocity plus acceleration times time, in which case we know that 0, or final velocity, equals our initial velocity plus negative 9.8 times t. And if you just actually solve that, you see you're going to have 25 divided by 9.8. So we're going to get the same answer as the trick. Okay, last part of the question. Let me group those together. Last part of the question asks, how long does it take to land? So there's another trick for this, and it's going to work because the rock starts and stops at the same height. So how long does it take to land? So we could describe this as time in air. And the time in the air to go up is the same as the time to go down. So we could basically, here's a trick, and just take the time to maximum height and multiply it by 2. I think this is going to give us 5.1 seconds in the air. So that's a trick. But if you have a situation where it starts and stops at a different height, or maybe you don't know time to maximum height or something like that, you can always take the given information that we have from up above and use, we're looking for time, so it'd be final position equals initial position plus initial vertical velocity times time plus 1/2 acceleration t squared. And it'll go like this. It lands on the ground. Final position is 0. It starts on the ground. Initial position is 0. Initial vertical velocity is 25. Time is what we're looking for. 1/2 times 9.8 is a negative 4.9, and t squared. So when solving for t, you're basically always going to end up with a quadratic. So you're going to need 0 on one side, and you're going to have to solve. You're going to get to solve. And it'll look something like this. Sometimes you'll have 3 terms, and it'll be the 2 parenthesis type factoring. But here we can just factor out a t from both of these terms, and we get t, and we get 25 minus 4.9t, and we'll group those together, and I think you're seeing at this point that we're going to get 2 answers. So from all that factoring you've done in math class, this tells you that t equals 0, and this tells you that t equals, and when we solve, it's going to be 25 divided by 4.9. Whoops. And that's going to give us 5.1 seconds. So we get 2 answers. It's like, well, which is right? What does that mean? It actually makes sense, because here's what's happening. Time t equals 0, that's right at the start when it had a height of 0. and 5.1 seconds later, that's right at the end when it lands. Thanks for listening.